Okay, let's review this problem. We have a gas mixture. We have a gas mixture of propane and air entering the chamber at the inlet number 1 and air entering the chamber at inlet number 2, and the mixture comes out from the chamber at the exit number 3. The mole fraction of propane and air at the inlet number 1 is 20% and 80%. So at the inlet number 1, we have this chamber. So this is the inlet number 1. Here's inlet number 2, and there's an exit number 3. And the mole fraction of propane is 20%. So at the inlet number 1, Y of propane, C3H8, is going to be 0.2, 20%. And the mole fraction of oxygen at the inlet number 1 is going to be 80% of 21%. I mean 21% of 80%. So that is 0.8 times 0.21. So that is 16.8%. So the mole fraction of oxygen is going to be 0.168. And the mole fraction of nitrogen is going to be 79% of 80%. So that is 0.8 times 0.79, so 0.632. So the mole fraction of nitrogen is going to be 0.632. So these are the mole fractions of each component at the inlet number 1. What about inlet number 2? We have air entering the chamber, and air is 21% oxygen, 79% nitrogen. So here, the mole fraction of oxygen is going to be 0.21. The mole fraction of nitrogen is going to be 0.79. And we have the exit. The mixture leaves the exit, and the mole fraction of propane is 3%. So the mole fraction Y of propane at the exit is going to be 3%, 0.03. And we have oxygen and nitrogen. Oxygen is going to be 21% of the air at the number 3. And the mole fraction of air at number 3 is going to be 97%. So oxygen is going to be 21% of 97%. So Y of oxygen is going to be 21% of 97%, 0.2037. And the mole fraction of nitrogen is going to be 79% of 97%. So 0.79 times 0.97. So 0.7663. So these are mole fractions of at each inlet and the exit. So let's determine the molar flow rate of the entering air at number 2. That means let's determine n dot number 2. Okay. So we can first apply mass balance equation. M dot number 1 plus M dot number 2 is going to be M dot number 3. So the mass balance equation, M dot number 1 plus M dot number 2 is going to be M dot number 3. However, we do not know the mass fraction between 1, 2, and 3. The only thing we know is the mole fraction. So let's convert this one into a mole fraction. So how can you convert this mole fraction, number of moles, molar flow rate, and the mass flow rate? We can use this equation. N is N over its molecular weight. If you have molar flow rate instead of number of mole, we can say N dot is going to be M dot divided by its molecular weight. So if you want to determine M dot, it's going to be M dot number 2 divided by the molecular weight at number 2. So this becomes M dot number 2 divided by its molecular weight at number 2. And this M dot number 2 can be found from this mass balance equation. And this molecular weight of this mixture can be determined by this equation. The apparent molecular weight, which is the average molecular weight, is going to be the sum of mole fraction times molecular weight of each component. So that means if you have a mixture of oxygen and nitrogen, its molecular weight can be determined by the mole fraction of oxygen times the molecular weight of oxygen plus the mole fraction of nitrogen times the molecular weight of nitrogen. So let's calculate that. Let's calculate M2, which is this one. The molecular weight at the inlet number 1, inlet number 2 is going to be the mole fraction of oxygen, Y of O2 times the molecular weight of oxygen plus the mole fraction of nitrogen times molecular weight of nitrogen. Then we know the mole fraction of each component, 0.21 and 0.79. Where can we find this molecular weight of oxygen and nitrogen? From table here, table A1. So these two can be found from table A1. The molecular weight of oxygen is going to be 32. Molecular weight of nitrogen is going to be 28.01. So this one is 32. This one is 28.01. And the mole fraction of oxygen and nitrogens are here. So this one is 0.21. This one is 0.79. So we can determine the molecular weight at the inlet number 2. That is 28.85. kilogram per kilomole. What about this? So this 28.85 is going to be this M2. What about this M dot number 2? We can find this M dot number 2 from this mass balance equation. So this M dot number 2 is going to be M dot number 3 minus M dot number 1. By the way, M dot number 1 is given. At location 1, at the inlet number 1, the mass flow rate is going to be 5 kilogram per minute. So this one is 5 kilograms per minute. So we have M dot number 1. We just need to determine M dot number 3. But M dot number 3 is not available. So one way we can determine M dot number 3 is finding the relation between M dot number 1 and M dot number 3. So what is it? At the inlet number 1, we have propane. At the exit number 3, we have a propane. And there is no propane at the inlet number 2. So the information about propane is going to be, what we need to determine the relation between M dot number 1 and M dot number 3. So what do we know? The amount of propane should be constant between the inlet and the exit. So you can say M dot of propane at the inlet number 1 is the same as M dot of propane at the exit number 3. However, we have no information about M dot of propane only. So M dot of propane is not needed here. Then what else? We can use N dot of propane. We can say N dot of propane C3H8 at the inlet number 1 should be the same as N dot of propane at the exit number 3. Because the number of moles of propane is constant unless there is chemical reaction, and there is no reaction. So the number of propane molecules should be the same as the number of propane molecules at the exit. So this is molar flow rate at the inlet and the exit in terms of propane. Then the molar flow rate of propane is how much? That is 0.2. 20% of N dot number 1 is propane. So the molar flow rate of propane at the inlet number 1 is going to be how much? 20%. So this is 0.2. 20% of the number of mole per minute at the number 1. So N dot number 1. So 20% of the molar flow rate at the number 1 is going to be propane. And 3% of molar flow rate and number 3 is propane. 0.03 times N dot number 3. Then We want to determine the relation between m dot number 1 and m dot number 3. And we only know the relation between n dot number 1 and n dot number 3. So if we convert this n into m, we can find the relation between these two. So how do we do that? N is m over m. So instead of n dot, we can say m dot 1 divided by molecular weight number 1 times 0.2. 0.2 is the same as 0.03 times m dot number 3, this one, divided by the molecular weight at the exit. Then we can find m1 and m3 by using this equation. So let's do that. N1 is going to be, what do we have at the inlet number 1? We have propane, oxygen, nitrogen. So instead of 2, we have 3. First, propane, Y of propane times molecular weight of propane plus oxygen, Y of oxygen times molecular weight of oxygen plus nitrogen, Y of nitrogen times molecular weight of nitrogen. That's how you determine the average molecular weight at the inlet number 1. What about at the exit number 3? Because we need to determine this N3 molecular weight at the exit. We can use the same equation. N3 is going to be, by the way, let's calculate this one. So the mole fraction of propane at the inlet number 1 is going to be 0.2. So this one is 0.2. The mole fraction of oxygen, 0.168. The mole fraction of nitrogen, 0.632. Then the molecular weight of propane, oxygen, and nitrogen can be found from this table A1. So we have propane 44.09, 44.09, oxygen 09, oxygen 32, nitrogen 28.01. So that's how you can determine the molecular weight at the inlet number 1. So if you do, we get 31.9 kilogram per kilomole. Then this one goes in here. Then let's determine M3, the molecular weight at the exit number 3. What do we have? We have propane, oxygen, and nitrogen. So the equation is the same. Propane first, Y of propane, M of propane, and the second component, oxygen, Y of oxygen times molecular weight of oxygen plus. The last one is nitrogen. So Y of nitrogen times molecular weight of nitrogen. That's how we can determine the average molecular weight. The mole fraction of propane first, 0.03, 0.03. The mole fraction of nitrogen is going to be 0.2037. The mole fraction of nitrogen is going to be here, 0.7663. Then the molecular weight of propane, oxygen, nitrogen, we can find them from the previous equation. So this one first, 44.09, 32, and 28.01. Then the average molecular weight at the exit number 3 is going to be 29.31 kilogram per kilomole. Then this one goes in here. Then from this equation, we have everything, about the relation between m dot number 1 and m dot number 3. So m dot number 3 is and this m dot number 1 is what? 5 kilogram per minute. So we can determine m dot number 3 from this equation here. That is 30.63 kilogram per minute. Then this value goes back to this equation here. Then we can find n dot number 3 and n dot number 2, which is 0.89 kilomole per minute. So this is the final answer. So this is what we did last Thursday. And let's look at the second problem. Second problem here, the mass flow rate of oxygen in the exit stream. So we have the mole fraction here, 0.2037 of oxygen, and we want to determine the mass flow rate of that oxygen at number 3. So let's do that. So we want to determine m dot, so this is part B, so this one was part A. So part B, we want to determine the mass flow rate m dot of oxygen only at the exit stream. Then do we know the mass flow rate of oxygen? The fraction of oxygen? No, we only know mole fraction. So let's convert this mass flow rate into a molar flow rate. How can we do that? Using this relation. N is N mass over molecular weight. This one again. So here, N is N over molecular weight. So if you add that, N dot is going to be M dot over molecular weight. That means M dot is N dot times molecular weight. So this one is M dot is N dot times molecular weight. The same thing. This oxygen, the molar mass flow rate of oxygen is going to be the molar flow rate of oxygen times molecular weight of oxygen. N dot of oxygen at the exit number 3 times molecular weight of oxygen. Then, do we know the molar flow rate of oxygen? We do not. However, we know mole fraction. Then how can we determine the molar flow rate from mole fraction? N can be determined by N of one component can be determined by the mole fraction times the total number of mole, because that is the definition of this mole fraction. Mole fraction is the number of mole of that component divided by total number of moles. So if you want to determine the molar flow rate, you can add a dot on top of it. And this one is for oxygen. So N dot of oxygen at the exit stream number 3 is going to be the mole fraction of oxygen at number 3 times the total number of molar flow rate at the exit number 3. Then we have the mole fraction of oxygen at number 3, which is 0.2037. So this one is here 0.2037. Then we just need to know the molar flow rate of the exit stream. Then how can we determine this N dot? Using the same the equation that we know, N dot is M dot over molecular weight. So let me write this equation here. N dot is going to be M dot over molecular weight. Then this one is for the exit number 3. So M dot number 3 is going to be M dot number 3 over molecular weight at number 3. Then we already determined M dot number 3 from here, 30.63 kilogram per minute. And we know the molecular weight at the exit number 3, which is 29.31 kilogram per kilomole. Then we can determine N dot number 3, this one. And do I have it? I don't. But once you know this one, once you calculate this one, it will go into this equation here. That will give us N dot of oxygen at number 3. This one goes back to this original equation here. And we already know the molecular weight of oxygen, which is 32 kilogram per kilomole. Then you can determine M dot of oxygen and number 3, which is 6.81 kilogram per kilomole. So that's how you determine the mass flow rate of oxygen at the exit number 3. Yes. So as a summary, we know the mass flow rate at the inlet number 1, right? That was given 5 kilogram per minute. And we have no idea about the mass fraction between the inlet and the exit. We only know mole fraction. So we need to convert this mass fraction into mole fraction. And how do we do that? Here. instead of, the studying mass fraction, we studied this, the molar flow rate. Then how can you determine this molar flow rate? Mass flow rate divided by molecular weight. And from this, we found the relation between m dot number 1 and m dot number 3. Because if you look at this, the molar flow rate, this molar flow rate should be determined by its mass flow rate. And the mass flow rate, we have no idea about m dot number 3. So to determine this m dot number 3, we use the relation between the molar flow rate at the inlet and the exit. So the problem is, we want to use this mass balance, but we do not know the relation between 1, 2, 3. We do not know the ratio between 1, 2, 3. Instead, we know the ratio on a molar basis. So we use this ratio on a molar basis into mass basis and then back to this equation to determine the molar flow rate. Kind of confusing, right? So we need to know either, we need to know either everything on a mass basis or everything on a molar basis. And there's no problem. The reason why you are confused, because we want to determine the molar flow rate, but the governing equation is mass flow rate, and the information that we can use to solve this governing equation is on a molar basis. So they are mixed up. So if you want to solve this mass balance equation, you cannot solve it right away because you have no information on a mass basis. But you have information on a molar basis. So here we convert between mole and mass to solve this equation, and then go back here to determine this molar flow rate. We use mass flow rate. So again, if I give you mass fraction of each component here, there, here, you can solve it without any difficulty. However, we only have mole fraction, and we want to determine the molar flow rate. The governing equation is on a mass basis. So there's a conversion here and there's a conversion there. So you have a, the double conversions are in there. That's why it looks complicated. So if you just follow, how I solved one by one, then you can solve it. You just need to get used to using this equation. N is m over molecular weight. So this problem is developed for you to apply this n is m over m in multiple locations. Here, to solve this n dot number 2, here, to find the relation between propane at inlet number 1 and the propane at the exit number 3. And the average molecular weight. To solve this n is m over m. So basically this problem is, just to you, the practice, n is m over m. Yes? Because there is no propane here. If you use the oxygen, you cannot find the relation between 1 and 3 because there is oxygen here too. The only, component, the only material between only at the inlet number 1 and exit number 3 is propane. So that's why you use the mole fraction of propane at the inlet number 1 and exit number 3. That's how we found the relation between m dot number 1 and m dot number 3. Any other question? I know it looks confusing, but this problem is, one of the things. I selected this problem from your textbook because it has a multiple n is m over m calculations, so you can practice. So let's go to the next problem. In this problem, we will also use the conversion between mass and the number of mole, because if you look at this, we want to determine the heat transfer and the work in kilojoule per kilogram. So we want to determine the amount of heat transfer and the amount of energy transfer by work on a mass basis. However, the information we got is molar basis. So again, the conversion between molar analysis into mass analysis. Okay. So we have a mixture, and whose molar analysis is 30% carbon dioxide, 70% nitrogen. So the mole fraction of carbon dioxide is 30%, 0.3. The mole fraction of nitrogen is going to be 0.7. So that is the ratio by mole between carbon dioxide and nitrogen. Now we have a cooling process from 425 Kelvin to 325 Kelvin, and it is constant specific heat. And we want to determine the heat transfer and the work each in kilojoule per kilogram. So how can we solve this problem? Since there's the cooling process, we need to come up with an energy balance equation. So let me write the energy balance equation. If you want to write an energy balance equation, there are two energy balance equations. One is for closed system, the other one is for an open system. Is it a closed or an open system? It's a closed. How do we know it is a closed system? You can check the mass of the system. This one is completely closed. So is there mass change? No, then it is a closed system. Then it is a closed system. What is the energy balance equation? We studied in Thermodynamics 1, the energy balance equation for a closed system is going to be Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1 plus moving boundary work. And then it's a cooling process. Therefore, there is a Q out. There's no Q in. And the energy transfer by work here, since there is no information about how this piston is connected, so the only energy transfer by work is going to be this moving boundary work. Then you can neglect the rest of them. If you don't want to use this mass times U2 minus U1 plus moving boundary work, if you have a constant pressure process, you can also use specific enthalpy, which is mass times H2 minus H1. So This one is the general energy balance equation. You can also use this form on the right-hand side. Either is okay because it's a constant pressure process. Then, to determine this energy transfer by heat, we can use this one, mass times H2 minus H1. But we want to determine this energy, the heat transfer in kilojoule per kilogram. That means you can divide each term by mass. So Q out minus Q out, by the way, lowercase q is heat transfer Q divided by mass, minus Q out is mass times H2 minus H1. Then how can we determine H2 minus H1 when we have an ideal gas? Ideal gas is a pure gas. So if you want to determine H2 minus H1, you can use specific heat. Oh, by the way, we divide by mass. So specific heat, Cp T2 minus T1. So this is the governing equation to determine the heat transfer. Then, what is the initial temperature? 425 Kelvin. What is the final temperature? 325 Kelvin. So, if you know the specific heat, you can determine the rate of heat transfer per unit mass. So let's find this specific heat. And according to this problem statement, it says that we need to evaluate the specific heat at 375 Kelvin. So let's find specific heat at 375 Kelvin. Unfortunately, we don't have 375. So we need to do a linear interpolation between these two numbers. Do we know how to do a linear interpolation? Yes, we do, right? So let's do the linear interpolation between these two numbers at 375. Since we already know how to do a linear interpolation, let me give you the value. For nitrogen, it's going to be 1.0425. 1.0425. And for carbon dioxide, it's going to be 0.917. 0.917. Then how can we determine this average specific heat between carbon dioxide and nitrogen? The specific heat of a mixture can be determined by mass fraction of each component. So in this case, carbon dioxide times specific heat of that component plus the mass fraction of the other component, nitrogen in this case, times specific heat of nitrogen. So that's how we determine the specific heat of this mixture. Then do we know the mass fraction? No, but we know the mole fraction. So here we need to study, how to convert mole fraction into mass fraction. So let's do that. Then we should make some assumptions. So 30% of the mixture by mole is going to be carbon dioxide, 70% is nitrogen. So why don't we assume we have 1 kilomole of the mixture. So this is the assumption. To determine the mass fraction, okay? So this is the assumption. We have a 1 kilomole of the mixture. Then what is the number of mole of this carbon dioxide? 0.3 kilomole, and the number of moles of nitrogen is going to be 0.7 kilomole because the mixture is 1 kilomole. So based on this assumption, the number of moles of carbon dioxide can be determined by the mole fraction of carbon dioxide times the total number of mole, which is, by the way, 0.3 times 1 kilomole. So the answer is 0.3 kilomole. So that is the number of mole of carbon dioxide. What about nitrogen? N of nitrogen is going to be Y of nitrogen times N. And the mole fraction is 0.7. And the number of mole is 1 kilomole. So the number of mole of nitrogen is going to be 0.7 kilomole. So that's how you determine N of each component. Then why do we study N of each component? Because we want to use one equation. What is it? This one. N is M over M. N is M over M. So let me use that equation here. N is N over M. So this one is what? N of carbon dioxide. It's going to be N of carbon dioxide, molecular weight of carbon dioxide. N of carbon dioxide over molecular weight of carbon dioxide. Similarly, N of nitrogen is N of nitrogen divided by molecular weight of nitrogen. So we are again using this equation. Then, do we know the molecular weight of carbon dioxide, the molecular weight of nitrogen? Yes. From table A1. There's a carbon dioxide. There's nitrogen. So this one is 44.01 kilogram per kilomole. And this one is 28.01 kilogram per kilomole. Then, can you determine the mass of carbon dioxide, the mass of nitrogen? Yes, we can. Mass of carbon dioxide is, if you do the calculation, 13.203. Kilogram. And the mass of nitrogen is 0.7 times 28. So 19.607 kilograms. Then you can determine the mass fraction. By how? Mass fraction is the mass of each component divided by the total mass. So this mass fraction, MF of carbon dioxide, can be determined by mass of carbon dioxide divided by the total mass. How do you determine the total mass? This one plus this. Mass of carbon dioxide plus mass of nitrogen. So we have 13.203. 13.203, and we have 19.607. So the mass fraction is 0.4024. What about the mass fraction of nitrogen? Can be determined by mass of nitrogen divided by mass of nitrogen plus mass of carbon dioxide. Then mass of nitrogen is 19.607, 19.607, 13.203. So the mass fraction is going to be 0.5976. From this analysis, we learned the mass fraction of each component. Now going back to this equation, .4024, 0.5976. Then the specific heat of each component. This one. For carbon dioxide, 0.917. For nitrogen, 1.0425. So carbon dioxide, 0.917. Nitrogen, 1.0425. So we have everything. You can determine the specific heat of the mixture. And that is 0.992 kilojoule per kilogram Kelvin. And this value, this one goes back to this equation so that you can determine Q out. So if you do the calculation, you get Q out 99.2. 99.2 kilojoule per kilogram. So this is the final answer. Any question? Yes. We determined Q out. So it's a positive. If you determine the net heat transfer, it's going to be minus 99.2. So the sign gives you the direction of energy transfer. If you determine Q net, it's going to be minus. If you determine Q out, that Q out already has the direction of energy transfer, so you don't need to worry about minus or positive. But that's not the end. We need to determine what? The work, the energy transfer by work. So how can we determine energy transfer by work? We have a constant pressure process, so the work can be determined by pressure times V2 minus V1. But we want to determine the work transfer in kilojoule per kilogram. So let's divide by mass. Then what do we get? Lowercase WB is pressure times V2 minus V1. Which is P2 V2 minus P1 V1 And since we have an ideal gas mixture, we can say PV is RT. So that is RT2 minus RT1, which is R times T2 minus T1. And we already know the temperatures. 425, 325. We just need to determine the gas constant R. How can we determine gas constant R? This R can be determined by universal gas constant R bar divided by molecular weight. Then what is R bar? Always 8.314 kilojoule per kilomole Kelvin. What about molecular weight? We know how to determine its molecular weight. We have a mixture. So if you want to determine the molecular weight of a mixture, Y of each component, CO2, times molecular weight of that component, CO2, plus Y of nitrogen times molecular weight of nitrogen. So the mole fraction of carbon dioxide, 0.3. The mole fraction of nitrogen, 0.7. The mole fraction of the molecular weight of carbon dioxide, 44.01. The molecular weight of nitrogen, 28.01. So we have everything. You can determine R. And if you solve it, you get minus 25.34 kilojoule per kilogram. So this is the energy transfer by work per unit mass. Why there is a negative sign? What does it mean? Having a negative sign. If a moving boundary work is positive, what does it mean? Expansion. So we calculated the moving boundary work is a negative. That means it's a compression process. So this is how you solve this problem. Any question? Much more interesting than thermal 1, right? No? More challenging for sure, right? Because it's the first time you are studying a mixture. And when you study a mixture, sometimes mass basis is convenient. Sometimes molar basis is convenient. When we have a single molecule system, like just oxygen, just nitrogen, then we don't need to worry about mass basis or molar basis, but now we have a mixture, so sometimes you have to use mass basis, sometimes you have to use a molar basis. So in the previous two problems, this one and the one before, all you studied is how to use this equation. Okay? So try to solve those two problems by yourself after this class to make sure that you are comfortable converting molar basis and mass basis. It is challenging for now because this is the first time you're converting these two. But if you keep solving those problems, then you will, it will be easier for you to convert between molar basis and mass basis. You need to be able to do them without any difficulty to solve, to study the next two chapters, moist air and chemical reaction. Okay? Because sometimes we are going to study on a molar basis. Sometimes we are going to study on mass basis. You cannot just select one and stick to that. You need to be able to study both. So it is pretty natural that you have a difficulty in these two problems. This is first time, okay? But that means that you need to practice these two problems that you studied today, which is one of the keys for your success in this thermodynamics 2. The actual governing equation in thermodynamics 2 is not difficult. There is no new energy balance equation. There is no new entropy balance equation. We are going to adopt the same energy balance equation and entropy balance equation you studied in Thermo 1. The only difference is that now you have a mixture. Sometimes you have to apply this energy balance equation on a molar basis. Sometimes you have to apply this energy balance equation on a mass basis. So the question is whether you are comfortable, converting between these two. So that's the difficult part. As you saw in the previous two problems, wasn't easy. So that was the part that many students, have a difficulty. So please solve these two problems. And if you have any difficulty, let me know. Okay, now we are going to study the real thermodynamics 2. Finally, after the 3 weeks. So we are going to study chapter 2 for moist air and chapter 3 for chemical reactions. And chapter 12, we are going to study this moist air on a mass basis. Nice, right? And then go to chapter 13. We are going to study this combustion on a molar basis. Okay? So we jump first. Chapter 12, moist air. Then let's study, how we can, let's learn, how we can, analyze a moist air. So moist air is a mixture of dry air and water vapor. So now we have a dry air and water vapor together as a mixture. So this mixture is what we are going to study using the energy balance equation, the same energy balance equation from thermodynamics 1. Okay, that means that we need to learn how to evaluate a property of this moist air. Okay, so let's do that. There are some assumptions that we are going to make. In moist air, the amount of water vapor present is much less than the amount of dry air. So our assumption is that the mass of water vapor, MV means mass of water vapor. So this V, water vapor. MA means dry air. So our assumption is that the mass of water vapor is much less than the mass of dry air. So you can say MV, the mass of water vapor, is much less than the mass of dry air, or you can use N instead of M. The number of moles of water vapor is much less than the number of moles of dry air. And our assumption is that since we have a lot of dry air and very small amount of water vapor, we assume that the mixture and each component, which is dry air and water vapor, they obey the ideal gas equation of state. So we are going to use the ideal gas equation. What is the ideal gas equation? PV is RT. So we are going to use this equation. And when you have a mixture, you may remember, when we use ideal gas equation for a mixture, we assume that each component, each gas, behaves as an ideal gas, as if each is alone at temperature T and volume V. So we are going to apply the same rule. We assume that dry air and water vapor as if they each exist alone in volume V and temperature T. But when we calculate the pressure of each component, we are going to use partial pressure TA, the partial pressure of a dry air, and PV, the partial pressure of water vapor. And when you combine these two, the sum of PA and PV, that is the gas pressure, the total pressure of the system. So when we say there's a moist air in this classroom, and that is about 100 kilopascal, that is this P. So there is partial pressure of dry air and partial pressure of water vapor, depending on the ratio between dry air and water vapor. So when we say 100 kilopascal, it is possible 70 kilopascal is the pressure of dry air, and 30 kilopascal is the pressure of water vapor. When you combine these two, 30 and 70, it becomes 100 kilopascal, which is the total pressure of this mixture, which is air and water vapor. And how can we determine the partial pressures? TA, the partial pressure of dry air, can be determined by YP. Y is the mole fraction. The mole fraction of dry air times the total pressure. PV, the partial pressure of water vapor, can be determined by the mole fraction of water vapor and the partial pressure, the total pressure. So that's how we determine the partial pressure of each component. Then the mixture pressure, which is the total pressure, is the sum of the partial pressures of dry air and the water vapor. So P is PA plus PV. So at the given temperature T, depending on the amount of water vapor in the mixture. So let's assume that the temperature in this classroom is 20 degrees Celsius. Depending on the water vapor, the amount of water vapor present in this moist air, there will be different partial pressure of water vapor. If you have less amount of water vapor present in this moist air, the partial pressure drops this way. You may remember, if we make this PTV diagram in Thermodynamics 1, if you make a TV diagram, the graph looks like this for given pressure. And when we talk about, the water vapor in moist air, that is this one, water vapor. Because this is compressed liquid, saturated mixture. Up to this point, you have liquid water, right? And you only have water vapor, whether it is saturated vapor or superheated vapor, right? So it's going to be either this point or superheated vapor. And P is the partial pressure of water vapor. So this P is going to be the partial pressure of water vapor, PV. and this PV goes down, this graph moves downward. If PV goes down, so if PV goes down, this graph moves downward. If PV goes up, this graph moves upward. So PV goes up. If it is at a constant temperature T, let's say this one, now this is important. If it is constant temperature T, this point, let's say that this is 20 degrees Celsius. The air in this classroom, there's a limit or of the water vapor amount this air can contain. What it means that at this temperature, this air can observe water vapor only up to this much. Where is it? At this temperature, your water should be on this line because this is the temperature 20 degrees Celsius. So water vapor in this classroom should be on this horizontal line. So if humidity goes down, that means you have a less amount of water vapor than the maximum amount. So the partial pressure of water vapor goes down. Make sense? Look at this one. The partial pressure of water vapor can be determined by the mole fraction of water vapor times the total pressure. So if the amount of water vapor goes up, the partial pressure goes up. If the amount of water vapor goes down, the partial pressure goes down, okay? So at this temperature, pressure should go up when you have more water vapor. That means if this is the air in this classroom, if you use a humidifier, then the amount of water vapor in the moist air in this classroom goes up, right? Then the temperature cannot change, so then it moves to the left-hand side. If the amount of air goes down in this classroom at the constant temperature, 20 degrees Celsius, then this one moves to the right-hand side, okay? So the amount of the air goes up in the classroom. That means the partial pressure of water vapor goes up. So from this PV to this PV and to this PV. However, the water vapor in this classroom shouldn't be liquid water, so they cannot be on this line or on this line. So the maximum amount of water vapor can present in this air is going to be this point when it is saturated vapor. So when we say 100% humidity in this classroom, that means the partial pressure of water vapor in that classroom is saturated pressure. If you decrease the water amount in this classroom using a dehumidifier, then pressure goes down from here to here, moving to the right-hand side. If you increase the water amount, it moves to the left-hand side, and the maximum amount is when it is saturated water vapor. Okay, so that's some the characteristic of the water vapor. We will continue this Thursday. Okay, thank you. I didn't know that it is already 1:50.